Hello, welcome to the stream. Happy Sunday. Hope you're having a good day. Today we are going back to implementing loops, and we're going to get to the meat of it today, I think, because last time we were dealing with the addition of side effects to the language, and before we had only one side effect, which was the read operation, and that one was. Early on in our development of this compiler, we got a note from the author of the book, which was pretty cool. But he was pointing out that you need to treat the read as side effecting, and so the order of operations matters there, and that meant that we had to do some of our transformations slightly differently. Well, in this one with loops, the whole point of a loop is to do things multiple times, right? So how do you, say, advance a loop counter? Well, you have to do it by side effect, at least in this construction, this language. And so we introduced set, which returns no. It's an operation that returns no value, but it modifies the value of an existing variable. So that means that we had to deal with set within the pass remove complex operands, and we have to treat it specially there. So we were working on remove complex operands. We're going to wrap that up today. I think we left it with a failing test, and I want to fix that test because we had different assumptions about how the transformation would play out, and we got a semantically equivalent transformation out of our pass that I think I convinced myself, it was either at the end of the stream or after the stream ended last week, that it was correct. So we're going to go forward with that, say, hey, this is fine, this transformation is fine. There's one other thing that I want to think about briefly, and so we'll look at the example in the book that was causing us these problems in our test. But yeah, let's go ahead and look at that real quick. So we're here in the book, right before section 5.6, and this is the example that we were puzzling over. So you have two let bindings, and then you have two nested sums. And there's this begin, which again is sort of a way to create sequences where you have any number of expressions, and then the final expression is the result of that begin expression. And it's basically a way to create things that have side effects, or that you don't actually care about the result of that expression. So here, they have parallel sets and gets, right? So here they're saying set y3 to read and get x2. So these are already bound to 10 and 0 respectively. And then in this one, it's like, hey, set x2 to read and then get y3. So they're kind of doing this crisscross, side effect thing. And the book says the transformation should happen like this. Obviously, it's because these are complex operands, you lift those into lets, and then you do the sum afterwards. So this temp6 is the sum of the inner expression, and then finally we're adding that inner expression to x2. So here they're putting x2 into temp7 and then adding those two. So that's the transformation they said should happen in the book. But we got something slightly different in our test. So I want to run the test again. And what we'll see is, because I made it, there's a couple of things here that are interesting. One is that there's a get here, but there's not one here. And the same here. And then this get also gets removed. So I wonder if there's sort of a if this is just a mistake in the book, or if it's if it's a situation where when it's in a tail position of some sort, then you don't need to use the get. Now this get bang, remember, was a marker so that we could treat variables that can be modified specially, right? So variables that are mutable in the presence, so we traverse the whole tree and look for sets on that variable. Ones that are ones that are mutated, you have to mark them with a get so that the sequencing of reads happens correctly. Okay. But it's interesting over here on the right that gets removed, and I don't know why that is. Yeah, weird. Maybe it's that. No, that doesn't make sense. I was going to say maybe it's that there are no further sets. So like on this one, x2, that doesn't make sense because it should be 10 here. If the order of operations is preserved, which it should be there, 10. And then you set x2 to later, to whatever is read from the console input. And y3 here was whatever was set here. So I don't know why those were removed in that pass. And it doesn't say anything about that in the discussion here. Let's reread this paragraph just to make sure we didn't miss it. Okay. So as usual, when a complex expression appears in a grammar position, it needs to be atomic. So atomic are like arguments to primitive operations, right? Must introduce a temporary variable and bind it to the complex expression. Okay, so this applies unchanged and handled in language form. So begin expressions get lifted. Right, the begin expressions have been bound to temporary variables. Let expressions in the monadic form are allowed to have arbitrary expressions in their right-hand side. So let's find a place begin there. So yeah, so this is what's interesting, is that I think let doesn't require atomic arguments. So we got a slightly different result here, and it's going to be a little bit harder to read. But did we pull that out into here? No. But this is the test that's failing down here. So we got a slightly different order. So we have x2 has an int 10, y3 has an int 0, which we expect. And let me shrink this over here so we can look at their example. Okay, and then there's a temp3, which is bound to another let. So this is where it gets a little bit different. And I don't think that we have a bug here, but it is curious that this didn't get flattened in the way you expect. I think what we were talking about last time is I was expecting it to come out in kind of 3-address code style, where you only have one binding. You don't have a binding that points to a binding. But that happens in a different phase. So then it's, read y3 and get x2. So that's this bit here. And that's being bound to temp1. And then temp3 is being bound. Let's see. No, okay. So okay, so temp1 is being bound to this begin expression, and then its body of the let is a let temp2, and then x2 read get y3. Okay, we know that the binding has to happen before the thing that follows, so this is okay. and then that its body is the sum of temp1 and temp2. So we get temp3, it's basically temp6 here, right? And these are temp1 and temp2, but they are inside this binding, basically. Okay, and then finally, let temp4 is get x2, so that's like temp7 here. I don't know why their numbers are different. I guess this doesn't matter, but for ours, they demonstrate the order in which we discovered bindings that needed to be created to remove complex operands. So, you know, being being kind of depth first, it makes sense that ours is temp1 and temp2 in these parallel expressions. So, yeah, depth first and left to right. So this is the left one, this is the right one of this expression, and so they get temp1 and temp2. And then, you know, get bang is not simple, is not atomic. Let's see. Yeah. Hello, welcome to the stream, Monte Cristo. Are you the sandwich or the count? Anyway, regardless, thanks for coming. Okay. Yeah, so it makes sense with our, you know, depth first, left to right, that these get temp1 and temp2, and then this expression gets bound to temp3. Yeah, so like I think that this is maybe a valid output, but it's not what the remove complex operands does in the previous, because like we haven't really changed the logic that much. We've just treated, and let me hide this a little bit so we can see. We have treated the new expressions as non-atomic, as complex, right? So if they're regular, if they're in the expression position, that's what this RCO EXP is. Then we just recurse into their contents. But if they're in the atomic position, like they have to be arguments to primitive operations. No problem. I love making content about Gleam, and I'm wearing my Gleam shirt today. I got it last week after my stream, so really excited. Okay, so in this case, you know, anything that's not one of these already kind of atomic expressions, we have to turn them into atomic and inject new bindings, and these bindings get returned to the outer scope, in which case they get wrapped around the thing that requires the atomic expressions. So that's how remove complex operands works. And you know, here it's introducing the variables, like all the return types of this need to be, what is the atomic expression to replace this complex one? And then what are the bindings that you introduce around that such that you can have complex expressions inside them? And then of course our counter. Our counter is like, how many temporary variables do we create? Okay, so that's how remove complex operands works. And I think, you know, this, I think that the actual is correct. And our assumption about how it would be constructed was incorrect, right? So we just need to fix our test assumption, which means we kind of need to rewrite this. Not fun, but we'll do it. We'll take the pain, and then we'll move on. Okay, so our outer one is going to be temp 3, and yeah, honestly, we just need to redo it. Can I collapse that and that so I can see what's going on? Okay, so let's look at our this is the one from the book, right? and we said, oh yeah, there's gets in there, but that's not correct. So what we think it, yeah, and this is not even correct. So maybe we write out what the correct way is, and then yeah, so we'll do let and this is temp.3, and that's going to have a let inside it as well. Okay, and that's going to have temp.1 is going to be the begin expression. It's going to be that. Too many brackets. Wishing for par edit as usual. Okay, I'm going to indent that so I can read. Okay, so there's the begin. This is the end of the begin, which means this bracket ends that let. Okay, and then inside here is let temp.2 begin, and that does this expression, right? Okay, and then here's plus temp.1, temp.2. And this follows the transformation that we would expect from this, right? We go in here, this is temp.1, this is temp.2. We've wrapped them in the order they were generated. So the bindings from the first sub-expression, the bindings from the second sub-expression, and then the actual expression that requires atomic arguments is the plus. So that's what gets put on the inside. And then the reason why we have the temp.3 here is that we're trying to make this sub-expression atomic. Okay, so we've bound this thing inside here to a temporary variable. And let me line those up roughly. Okay, so this actually goes on the end here, like so. This is not going to be exact because I'm not actually trying to check it. And then this will have, remember this gets marked because x2 is mutable, it gets marked with get bang, so that needs to be let bound. So that's let temp.4, and that's the get bang of x2. Okay, and then finally you have plus temp.3, temp.4. Okay, so this is what we're going to get transformed into. This is what the book says, and we're going to axe that. Wait, this looks like what we... This looks the same. What did I do? This is what it actually produced. Okay. Well, there we go. Okay, so we're going to reproduce this one because I just redid it and I thought, oh, this one's wrong. No, it's actually what was before. Okay. So temp.3, we have a let of temp.1. And that's going to be begin. Nope. Begin, please. Okay. And that's going to have set of y3. Primitive read. Okay. And the trailing expression is going to be get bang x2. And I just want to get this, indented to where we can read it later. The formatter will probably indent a lot more for us, but okay, so that's the binding, and then oops, Yeah, that's the end of the begin. Okay, so then in here we have let of temp.to, and it has a begin. And I think I'm gonna resize here, and we'll get a split going on so we can see this. So I'm glad you came for the Gleam content. One thing that's been nice about Gleam in this particular application has been that when I make a mistake typing out these ASTs manually, the type system will tell me. So you can see here, it's like, hey, you know, this let expression expected 3 arguments but got 2, and it takes binding expression and var, these labeled arguments. So yeah. Okay, so temp.to, let me scroll up here. So it has a begin, and it has a set bang of x2, and then the read operation. Okay, and then it has a get bang of y3. Okay, and then finally here you've got a primitive of plus, and this has to be atomic, remember, so this is var temp.1 and var temp.2. Okay, so now we have bound temp3. So what do we do in temp3? After temp3 is bound, we do another let. Temp.4. And this is going to be get bang of x2. And then finally we have the tail expression. It's a primitive operation of plus. And let's get these on new lines here. All right, this is a little tedious, but we're at the final, we're at the end here. So temp.3 and variable temp.4. Okay, so now no more squigglies. And we have our fully indented thing here. Cool. So let's run that test and see if we got it right. Okay, so again, you know, I would love for us to be in a situation where we could write the test with like perfect knowledge of what the answer should be and then see if our code is correct. But as is the case with other kinds of development, I often find that I will have to check my assumptions, and sometimes the test I write is not correct, and the code is still correct or acceptable at least. So this is another case of that. We misunderstood the order of operations here, and we were a little bit misled by what was in the book, because the book, this is like heavily flattened in a way that, I say flattened, it's like nested with only one branch, right? Whereas ours actually is nested with 2 branches. There's this branch under temp3, and then there's the top level branch. And this one does make sense. You could transform it such that these lets happen above, and then temp3 is this, right? Which is ultimately what you want it to be. But remove complex operands never did that. Like, that was never part of its charge. The explicate control was usually the thing that did that. So it makes execution order explicit. And here we even have, I think we have some examples that are interesting. So note here, this is why explicate control does this, right? This is y is bound to this let expression, right? All of that. And then what explicate control does is turns it into this. So that the order of bindings is explicit rather than this kind of nested doodad. So that's what we'll do in the next phase. Of course, we need to deal with loops, which is the whole point of this chapter. But I think it was unreasonable to expect remove complex operands would turn this into this. It doesn't. And heck, even the thing that explicate control doesn't completely eliminate nested lets. It just makes their order really, really explicit. So honestly, I think we were okay, and actually explicate control might not even change what we have. So we'll see. All right. Okay, so now that we fixed that, let's make a commit. Fix remove RCO test. We'll just call it that. And we have our our tests on GitHub failing. So I feel confident with that. We need to, before we go on to explicate control, we need to jump back to a phase that is supposed to happen before it, and that's shrink. Shrink is supposed to happen first, and the point of shrink is to turn and or expressions into ifs. So we didn't update it for our new input language. So I think what we need to do here is we just need to rename this to while and see what breaks, right? So so what expressions do we not need to go dive into? Well, let's just go ahead and add the missing patterns, and we will, because we are in the business of importing these while loop, we'll just import them. Begin, and then we'll remove the qualification there. Oops. Okay. So here we need to do begin list.map of statements with shrink expression. I think we can do it like so, and then we'll do shrink expression on the result. Lists. We need to import Gleam lists. Gleam list. Okay. And then on setBang, we need to just return setBang of var and shrink expression of value. Shrink. And then while loop, there's a question in my mind about the condition, whether this is going to introduce anything weird. It might not. Let's just, damn the torpedoes. These are all expressions, so okay. And let's see here. There's one more primitive operation, which is void. So we need to import that. And honestly, that just, there's nothing to do there. That's prim void. This is like not strictly necessary in the language, but technically you need to have something that can construct the void value according to their design. So, okay, so we fixed shrink. Let's look at the shrink test, and we just need to while this. So this is, we've got a problem here. Oh, yeah, so we renamed those to Boolean T and integer T just to distinguish them. So that's really, that just got renamed. So we need to find those places where, yeah. And this is just validating the type checker. I think that the point here was that the shrink phase didn't, like, even though it mutated and operations and or operations into ifs, that it didn't change the semantics of the types, right? So that was the point of that test there, and I think that that's a good thing to update. I could have named those variants differently, but here we are. Okay. So let's run our tests again, make sure we didn't break anything. What is not used? Oh, select instructions. Yeah, we're not there yet. Okay, so update shrink phase. Okay. That is something that we did not do previously, so it's good to get that out of the way. All right. So now let's look at explicate control, which is the whole goal of today. Thank you. We're already half an hour in, and we're just getting to the meat of it. So let's follow along with what they're talking about. Explicate control is, again, about turning this into a C-like language. It's not really C, but it has semantics that are closer to C, which means that when we get, so rather than being expression based, it's statement based, and that transformation was kind of a brain bender the first time we wrote it, but I think I'm getting more comfortable with it as we go. But what they're saying here is that we define a function for every position within the program. So if you look at the version that we had before, this is turning the monadic form of the Lispy language into a C-like language. So this is making the execution order explicit, basically as a graph with go-tos. Okay, so we have like this recursive operation to generate this, and it starts with the tail. So tail position is saying this is the result of the entire program or the entire nested expression, right? So if something is in tail position, it is a return value, essentially. So the return value of the aggregate, or the position of the aggregate expression, which is the entire program, is the tail. And then the last expression that will inside that expression will be also in tail position. Okay, so when you're doing explicate tail, it's about making sure that you are returning something. Okay. Um, right. So then this is we're constructing a program, which is C-like, and we're going to have to make a new variant of C. So we had C-var, which has, has variables. C-if, which has if expressions and branching, or if statements and branching. And now we're going to add loops. So we need like a C loop, right? So I'm going to start by duplicating C-if, and I'm going to rename it to C-while. Or C loop. I guess we could call it C loop. Okay. Now we need, so here in C loop or C while, let's call it loop. I'm already like C loop. We are going to have void is an atomic. So void. Interesting that they're making read be a statement. I'm curious why, because it was a primitive operation before. Is this a typo? That doesn't make sense to me. Maybe we'll need to read the prose to find out. Okay, and then the C program is basically the same. Note that there's no while in here. The loops are turned into go-tos and ifs, right? Which makes sense. So Ethan, welcome to the stream. Is this a parser of sort? No, this is a compiler. We do have a parser in it. So we have this parse pass, which is using Nibble by Haley. If you are familiar with any of the Gleam ecosystem, Nibble is a pretty neat library. So we do have a parser, but we're actually, the goal of this is we're going through this book, and we're on page 94. It is called Essentials of Compilation. This is the repo that we're working in. It's public on my GitHub, and you can go to the source material as well. So this is where we got the book as a PDF. I also have the physical copy, which I love, but it's kind of hard to look down at the book and in the physical copy and go, yeah, look at this paragraph, and it's easier to use the PDF when we're on stream. So let me see if I can jump to 94. Yeah, okay. So that's what we're doing. We are in chapter 5, which adds loops to the language. So we started off with a language which just has integer arithmetic, and then we added variables, and then we added conditionals, and now we're adding loops. So like this is a very incremental type of building up a compiler, and you go all the way down to x86 assembly. So it's not just, oh, build the front end and parse these features and do semantic analysis. You do that, but your goal is to create valid x86 assembly. So we can do that already with our previous phases. All right, you're welcome. No problem. I'm always happy to clarify, and thank you for coming to the stream. Really appreciate it. Okay, so we've got our C loop language. Oops, and there we go. Okay, so it adds void, and I don't understand why this read became. See, it's up here, but then they put it here too. I really think that that's like a mistake. I don't really understand. Okay, we're going to ignore that for now because I don't think that that's a meaningful change. I guess you could read something and throw it away. But you notice previously statements were assign a variable and expression. Maybe they meant, no, begin doesn't make sense here. Okay. Well, I guess we'll find out. So let's look at the text here. Okay, so again, we were talking about the different positions. There's tail position, which is the return value of the program. There's assignment position, which is that this expression needs to be assigned to a variable, right? And there was one more, which was, oh, no, not yet. Oh yeah, predicate position. So this is an expression which is being evaluated as the conditional of an if, right? So, and it has some branches for the true branch and the false branch. So that's predicate position. We're going to add one here, which is going to be effect position. So, okay. Right, so for LVAR, we needed assignment and tail positions. If expressions introduce predicate positions. For LWhile, the begin expression introduces yet another kind of position, the effect position. So except for the last sub-expressions inside a begin are evaluated only for their effect. So it's basically like we're going to do those things, but we're going to throw away their return values. The result values can be discarded. So we can generate better code by taking this fact into account. Okay, the output language of explicate control is C loop, which is nearly identical to C if. The syntactic differences are the addition of void, and that read may appear as a statement. Okay, so I think that they're saying here that the reason read can appear as a statement is probably that it can be in effect position. The most significant difference between programs generated by explicit control and chapter 4 is that, okay, so control flow graphs in chapter 5 can contain cycles. In 4 they could not, and that actually made certain things easier. We could build the graph, use a topological sort to determine the variable dependencies, and then use that to assign registers. Okay, so the new auxiliary function explicate effect, which we're going to write, takes an expression which is in an effect position. So basically you're saying only inside a begin, and the code for its continuation. The function returns a tail that includes the generated code for the input expression followed by the continuation. Okay, if the expression is obviously pure, that is, never causes side effects, then the expression can be removed. So the result is just the continuation. That's interesting. We'll probably figure out as we build this what that looks like. The case for while loop expressions is interesting. The generated code is depicted in the following diagram. So there's a goto loop, and that loop is, it's a label. It has a condition. So there's an if there, right? If that condition is true, then you do the body and you go to loop. Else you go to the continuation. So we generate a fresh label loop for the top of the loop. Next, you recursively process the body in effect position with a goto loop as the continuation. Okay. So right, so this is condition. Condition gets a block, body gets a block. And the continuation, okay, and the continuation block as the else branch. Results should be added to the dictionary, right? Okay, with the label loop. The result for the whole while loop is a go to the loop label. Okay. Auxiliary functions for tail, assignment, predicate need to be updated. The new language forms while, set, and begin can appear in assignment and tail. Only begin can appear in predicate positions, with the other two have result type void, right? So if we get while set in a predicate position, we should panic, because that's a bug in our compiler, or it's a bug in the input. But I don't know if there's a... No, we would type check that. If we type checked it, while returns void, set returns void, those should never appear in conditions, because they would return void t as the type, and you need boolean t in a conditional position. So, all right, well, let's get started. So C loop. It's interesting they put prim read here. I think that we just want to have a new type of statement, which is read statement. And again, this is so that you can have effect position, a read statement in effect position. And the only reason that has to exist there, because like obviously if this is not being assigned to anything, it's going to be thrown away. But read is, read something from the user input, right? Read an integer in our case, because we don't have any other data types that can be read. So read an integer, that doesn't represent something that's actual input, but it does represent an interruption, like a pause in the program. You're waiting to read from the console. So that makes sense, I guess, in that it's something that would be in the sequence of statements, but we don't care about the result of it. If we cared about the result, it'd be in an assignment, right? It'd be an expression over here, and that expression would be a primitive operation, which is read. But we're not assigning it to anything. It's just... It'd be like if you wrote, like here, if you wrote begin read here, like it's totally fine to put that there, but it doesn't result in anything. It just results in an interruption in the flow of the program. So I get it now. Okay, so first of all, we've got to do some cleanup here. This is assuming that we're using the C if language. We're going to be using C loop. So I think what I want to do is we're going to introduce an alias there, and then we're going to find, oh yeah, and we're going to find all the places where we have CIF qualified, and we're going to replace them with C dot. I forgot there's a Gleam 1.12 out today or yesterday, and I did not update to it. Okay, so this will make it easier to switch to our new languages, right? So we're going to do the same here. We're going to say this is L, and we're going to say L if, and that's L dot. So let's replace all. Okay. And then Lmon if as Lmon. The only reason we have this one is that we defined some types in this, and we didn't want to do a lot of conversions, so we just pulled them through and reuse them. We're going to replace that with Lmon. Okay. Replace all, please. Okay, so now we can go, this is C loop, okay? This is L while, and this is Lmon while. Oops. Okay, so now we're going to have some errors, of course, because we're not handling all of the expressions. Okay, so what do they say we need to do? fresh label. Okay. So we're going to have to create explicate effect. And let's put it above create block. Explicate effect. And explicate effect takes an expression in an effect position. And a continuation. So what were we doing for continuations in the other ones? It's a tail, right? And there's going to be blocks. Oops, I'm editing the wrong function. Explicate effect. So tail is a c.tail. This is continuation. And this is going to take blocks, which is the blocks. And it's going to return, so they're saying it returns a C tail, but we also created blocks here potentially, so we need to return those. Okay, so explicate effect takes an expression, code for its continuation, returns a tail that includes generated code for the input expression followed by the continuation. Okay, so if the expression is obviously pure, right. Okay, and then we need to handle the other cases here. So here, this is a simple one. If we have void, we can convert it to C void. There's obviously like nothing that does useful. But we have that. Okay, so I think what we can do we could implement explicate effect first and then go back and fix the others. But maybe we go up here and say we look at the different cases here. So we're going to have to add this. What did I do wrong there? Okay. No, there needs to be 3 parens. Huh? Oh, it's because void doesn't have any arguments. Okay. Okay, so we need to handle right, so in tail position we need to handle the other cases. So let's see if the add missing patterns. Okay. So we'll need to handle begin directly. So let's look at, they said something about tail position. Right, so they can appear in assignment and tail positions. Only begin can appear in predicate positions. The other two have the result type void. Right, so I think what we do is so for begin, we need to let's handle that one last, I think, because what we'll do here is we'll do explicate pred on this. We'll do explicate tail on this. So let's do get bang and set bang. This is basically the same as the variable atomic up above, right? So this will be c.return, c.atom, c.var, variable var, and then blocks. Okay. For set bang, we have c.return, c.atom, c.void, and blocks. Now we need to this is basically like a let. So we need to right, so we need to do something like this actually for set bang. That's fine. What we'll do is yeah, so we we don't need to explicate tail, we just need to explicate assign, and we'll give it the tail. Okay. So we'll just say let tail is this. We'll pull it out. And we'll say explicate assign. And this takes value, explicate assign, and the string is the variable, takes the tail, and the blocks. Okay, so that wasn't too bad. Basically, we're just making sure that this gets turned into assign something to this variable. Now, it's not actually that useful because you're assigning the variable and then you're just ignoring what it is. But if set bang is in tail position, then that's what you do. Okay, so yeah, we'll do while loop last. Let's do begin. And let's do we need to think about kind of unwinding this similar to what we did in remove complex operands, because what you want is this list, because it's a list, it becomes a nested tail, like, because your tail here is, well, I guess it could be sequence of statements and then tail. Okay, so we can do that. I'd forgotten that we had that with if. That's actually really great. Okay, so for begin, what we will do is the thing with this is it needs a continuation, right? I'm forgetting the case where we generated a sequence before. And we're like down here, right? Okay, so it's generating a sequence of assignments. And then the tail is the continuation. Okay. I mean, I guess that's what it is. Okay, but hold on. This is a single statement, not a list of statements. So we kind of need to fold building that up. Okay, well we need to generate the tail, right? So explicate tail takes the expression. So we need to explicate tail first, right? So this will be tail and blocks 1, right? Because this is in tail position, the begin, the result, the last expression inside the begin is the result of the begin expression. So that if this is in tail position, then this is in tail position. But these are in effect position. And I feel like we should sort of fold right. Because, for each one of these, yeah. Let's see what they say about explicate effect. Takes an expression and the code for its continuation. Right. Okay, so we're going to do yeah, and it returns a tail, right? So we're always generating a tail. Yeah. Okay, so what we're going to do is we're going to fold right. We're going to fold right over statements. And let's see, statements, right. So fold right gives okay, so our accumulator needs to have this tail and blocks 1. So we could actually just inline that. And then it's going to call explicate effect. And we need the order of arguments to be correct there. So that function needs to take, yeah, so we're going to wrap this. Accumulator and then statement. And we're going to call explicate effect statement. And then the accumulator, let's see, explicate effect takes, hello? expression, a tail, and the blocks. Okay, we could do that with or use rather. We could do like use accumulator statement and do list fold right. But I'm not going to do that today. Okay, so the point here is that this result is the continuation for the statements going backwards, and so we want to build that up from right to left. Okay, so now if the while is in tail position, we need to basically generate this. So we need to break these into blocks. Let's look at how we compiled if. It's like explicate tail for the if true, and then explicate pred. Okay, so I think we can leverage explicate pred, right? Based on this graph. Okay, let's look at tail position. Can be in a go to, if, a sequence, or a return. Okay, let's split right, and so we can keep that over here. So if true and if false are tails. Let's look at explicate predicate. Okay, so there's the conditional. Okay, so our if false is basically return void in tail position. So let's write that down. Right? That's our if false for the condition. And we need to create a block for that. Yep. Okay, so that's what it's going to jump to when the loop terminates. Then we need to create a block. The interesting thing here is this is explicate effect. So when we create block, oh, we need to, we need to generate a fresh label. Yeah, so I think our existing create block is not going to work. So let's make a create label, which takes, I'm going to take a prefix, it's a string, and the blocks, and it's going to return that string label and the updated block, except it doesn't update the blocks. Does it? No, it doesn't, because we need to put something in it. So this is like, give me a new label. And we'll pull this bit into here. And this will be prefix. We'll do it like so. That's not great, but if we're careful how we use it, and this is going to be block and blocks. Then we can create the label before we have the thing it points to, if that makes sense. Okay, so where were we? Right, so here we need the loop. Loop start is going to be create label, and we're going to say loop, and we'll pass it blocks. So that doesn't modify the blocks. But we do need to create a block. Or rather, the loop tail is going to be go to loop start, right? That's what this is. That's what I'm trying to get to. This is also going to be the loop beginning. So the result of the while expression is go to this loop. Okay. So you have to create this label before you can jump to it. And because we're cyclical here, like, we've got to deal with those things slightly differently than we did before. Okay. So this is not the loop tail. This is the, we'll call this loop label, loop start. Okay. So we know that if we, so when the loop terminates, we need to jump to this return void. And that's what this if false. So we have an if true, blocks 2. We need to explicate effect on the body, right? We may have to do some like manual manipulation of this thing as well. Okay, so we need to explicate effect on the body, and its tail is go to loop start, and it takes blocks 1. Okay, and then we need to insert the loop conditional. And we'll give it this label. I think this is the hardest thing we've done so far, and I'm sorry if it doesn't appear like that, but okay. So let's say the loop condition is going to be we need to call explicate predicate, right? And we give it the if true, if false. Now it's going to return an expression, right? We've already created blocks for these things. Potentially. We did for that, the if false. Maybe we didn't need to for that. Maybe we just need to call explicate effect on the body. Yeah, I think that's okay. We can get rid of this. So explicate effect will actually create a block for this, probably. Maybe not. Okay, so the loop condition is going to be explicate predicate, and the expression is going to be condition. And then we need the if true, right? That's a tail. We need this is the if false. And then we need to pass blocks 1. Okay, so now we've got, so loop condition is so that's the tail that we want to jump to. And I think we're just going to do something like this. So we're going to insert into blocks 2 loop start. No, loop label. And we're going to give the loop condition. Okay, so now we have, so we can get rid of this line. Or honestly, we can just pull it up and say let if false that's going to be that tail, and that'll make this a little bit simpler to read. Okay, so we created a label, and the jumping to the start of the loop is this loop start statement. Then we say, you know, if, because this is in tail position, we have the if false is return void. And then we have to say, well, the body of the while loop is an effect, right? it doesn't return anything. It doesn't evaluate to any value, and so those are all in effect position. But that's what you jump to if the condition is true. And then we will treat the condition as a predicate in predicate position. So we'll evaluate that, or we'll explicate that condition and jump, to either the body or to return void, and creating any blocks as necessary. Then we're going to insert the loop label. So this is the thing we want to jump to at the end of the body. We're going to insert it into the known blocks with that label that we created, and with the condition. And then what we're going to return is a tail of loop start, because that's what we're going to jump to, right? And then the updated blocks. Okay, so hopefully you all followed that. So we had to make a few changes here, and it says create a fresh label for the loop entry point. Jump to the loop entry point at start and bottom of the loop body. Okay, and then this is tail position. I'm just going to write this out so that we record what we learned. So, and while loops have the void type, the body does not affect the return type, so it is in effect position. And then the loop condition is in predicate position, so we have to do that. Jumps to the return if false, otherwise executes the body. And then finally add the entry point of the loop to the blocks, and then finally jump into the loop. Okay. All right, so that's what we were doing there. We've got explicate tail done. It's not showing any problems there. We need to go into explicate assign, and let's look at what we got here. So these can appear in assignment and tail positions. Only begin can appear in predicate positions because the others have type void, right? So maybe what would be simpler to do is go down to explicate pred, and it looks like we have some other things to fix here. Define a while. I don't know why. Maybe we need to restart the language server. We've done enough changes that it's getting a little bit messy. Okay, yeah, let's go to explicate predicate. Sometimes the folding there is weird. So c.comp. Oh, right. So what we need to do here is we need to say this is a while type comp, and then that'll fix those problems. Honestly, at this point we've like reused that so many times. I'm tempted to make like a utility module that just has that comparison type in it, and we just reuse it everywhere. uh, okay, so in explicate pred, so this is, we were panicking for unhandled cases, which is fine, but we need to introduce a begin case. And result. Okay. So I think that this will be similar to what we did in tail position. So let's just copy that. And that's going to be explicate pred on result. And do we need to create blocks? I don't think we need to. I think we can call explicate pred and just pass along the continuations. So whatever is inside that, yeah, let's look at some of the other things here. So like if it's an atomic, you know, with a variable, we do create the blocks there. And then, you know, of course, invert the branching there if it's a not expression. Yeah, so we don't need to create blocks in this case, I don't think. Eventually, we will be turning this into an if for one of these other expressions. Okay. That was pretty straightforward. Again, remember we are like folding over these statements that are in the begin because they have no output. They're only for side effect. So that's what we're doing there. I think that handled the case for explicate predicate. And then while set and begin can be, okay, so only begin can appear in predicate position. That's why I did that one first. So while set and begin can appear in assignment positions. Now, the other thing here that we need to handle, I believe, do we have a get bang? I think we have get bang. We do have get bang. So I need to figure out, did we handle that here? Yeah, we handled it in tail position. Okay, in predicate position, I think it's equivalent to an atomic variable. So I'm going to do that. Remember, that's not for this. We've already we're figuring out the sequencing. Or rather, we used the get bang in a previous phase to make sure that we don't get the order incorrect. So I think that this is safe. I can't imagine it would be work any other way. Okay. Yeah, so we should expect a panic on any of the others there. Yeah, like those are not valid in predicate position. That's why they're commented out here. We can say lmon.while loop and condition body, right? That's not valid. lmon.setBang is not valid. Var expression, right? That's not valid. Okay, so that's just to be consistent there. All right. Let's do explicate assign. So while and set can appear in assignment and tail positions. Okay. So let's add the missing patterns. So again, like we may have up here at the atomic, variable or integer or Boolean, honestly. So I think what I want to do is put a case up here. Well, let's just copy this case, right? For get bang. And what we're going to say here is this is c.variable var. Okay, and then set bang. It's kind of weird that you would assign well, this is actually really straightforward. It feels weird, but it's going to be straightforward. So let's just do it. And I think we can do it like so, because it doesn't need to create any blocks. So we'll have a sequence of c.assign. And this is... what we need is a new continuation. Oh, right. So we assign void right? To we assign void to the variable because setBang returns nothing. It returns, its return type is void. So our input variable gets assigned void. And then we do explicate assign again on that because that's the continuation for, so we're going to remove the brackets here because what we want to do is explicate assign. What is that? What arguments does that take? Hello. It takes an expression, a variable, a continuation, and blocks. So this is the continuation, the new continuation. And we'll put curly braces around that. I just want to make sure that I'm not like getting my stuff confused. So value is the expression, var is the new assignment. We have the new continuation, and we have blocks. Did everybody follow that? Basically, so what you're saying is you have something that looks like v is setBang of something, right? And then you have the continuation. So what we want to do is turn this into, so this becomes v is void, and then, so this is v1 some e, so v1 equals e, and then that's what we're doing here. Okay, so this becomes the new continuation for a new assignment, and that's what setBang does. Okay, so now begin. We're gonna have something similar to what we did before with the fold right. So let's say let new continuation is going to be explicate assign, and that's going to, we're going to do result here, right? Result is var and the original continuation and blocks, not var v. So our v is our input variable, or a thing that we're going to assign it to, and then we do list fold right. And this, by the way, is going to return blocks 1. So we're going to fold right over statements, and our accumulator our accumulator is this, and then we'll do that statement again, and this is going to be explicate effect of statement, and is that how I did it? Yep. Okay. So you can see patterns starting to emerge here. So in assignment position for the while loop, I think that we'll copy the stuff we did above, because we still need to create. The weird thing here is, like, you'd say, oh, this is an assignment position, but you're just getting void, so why don't you just toss it out? We don't know yet that the contents of the while loop aren't used for side effects. And this is where it gets messy, right? So what we're going to do is, rather than return void, we're going to say this is... we're going to do explicate assign. See, if false is a table. Okay, so we're going to assign void to V, and then the continuation and the blocks. Oh, this... Is that not an expression? No, we want L.atom, right? Oh, for Pete's sake. Come on, Sean. All right, what expressions do we have over here? It's just prim void. Oh, we want Lmon prim, Lmon void, right? There we go. Finally got it correct. Okay, so this will be blocks 1. We'll do blocks 1. We'll renumber things here. Blocks 2, blocks 3, blocks 2, blocks 3, blocks 4. Okay, so again, we're doing the same thing that we did before. Where in assignment position, the ultimate outcome of this assignment is to assign void. If while loop is on the right hand side of an assignment, you get void for that variable. That's just what the types are. But you still need to execute the loop. So we have the expression gets replaced by jump into the loop. Of course, its continuation is, make this assignment. And when the loop ends, it jumps to the if false of the condition. So I feel good about that. And I think our last bit is really explicate effect, and then we can wrap up for the day. And maybe we'll have time to write a test. Okay, so we basically need to right, so if the expression is obviously pure, that is, never causes side effects, then the expression can be removed. So the result is just the continuation. Okay, so let's just let it fill out all the patterns for us. So we know that so in effect position, in other words, this is statements in this section of begin. In effect position, we know atomic, because that's just, read a variable or a constant, right? That has no change to things. Get bang has no change to things. Actually, let's just start to combine these as we figure them out. Primitive operations are also, we can just make these underscore. Because at this point, we have, in remove complex operands, we made sure that primitive operations only have atomic arguments. So this can have no side effects. However, all of these other things can contain side effects inside them. So let's figure these out. Okay, let's start with set bang. What we need here is a tail. Remember, set bang is the same as assignment, so basically the same as let. What did we do up here? Right, so the continuation is... Right, this was in assignment position. What about in tail position? Yeah. Okay, so we do need to do explicate assign. So we're going to do explicate assign. And that's going to take values of the expression, var, and the continuation is this in blocks. Okay? Pretty straightforward there. Let's look at let. I think this is the same, basically. What do we do in explicate tail for let? All right, you do explicate tail on the blocks, or on the expression. I think what... Okay, so this is kind of what we need to do, except because we're in effect position here, we do explicate effect. And we pass it the continuation. This is expression. And then we do explicate assign. For, what does that take? Binding variable. Okay. That makes a sense. That makes sense. And like the point here is, since you're in effect position already, the value of this expression is going to be thrown away. So you only care about side effects. So this is an effect. And we're going to have to do the same here with begin, right? So again, we're going to do that loop thing that we did before. So this is let tail blocks explicate effect of result, continuation, and blocks. And then, and actually we're just going to, we'll call it this. We're going to fold over the statements, taking the tail And this is the accumulator statement, and we'll do the same dang thing we did before, explicate effect for the statement, and 0, 1. Okay, if gets kind of interesting. If and while will be interesting. So I feel like okay, so yeah, what we need to do is go similar to what happens up here in tail for if. Right, so this will be explicate effect, and then explicate predicate. So this is going to be... The thing is, we may have to create a block for the continuation. Let's see. Where are we creating blocks? Okay, we create a block in assignment position, but we don't do it in tail. I guess that makes sense. So we need to create it in effect position. Yep. So we're going to do... Okay, I'm going to shorten this because I don't want to type all that. Okay, so because what we want is both these branches to jump to the same thing, so we basically have to create a label for them. Okay, so explicate effect, we take the if true, which is an expression, and its continuation is the new continuation, and B1, else block B3, and if false, new continuation B2. And then finally we do explicate predicate. And we pass the condition, and that takes the then block, and the else block, and the collection of blocks. Okay, we're in the home stretch here. Let's keep going. So I think we're going to have, we're going to do something similar here, right? Except that these cases where, so that was an assignment position. The if false is going to be explicate effect, as well as the if true, right? Wait, hold on. Yes. All of these are in, The thing is, though, for the while loop in effect position, I think what we do instead of, because we don't need to create another effect. So here, let's make sure that the comments are correct up here in explicate assign, because this is assign position, right? But in effect position, we could throw out anything. So what we want here is we just want to create block where we pass the continuation and blocks, and then that's it. This is effect position, so just jump to the continuation at the end. Okay. And I think we did it. Woohoo! Wow. Okay. So we need to write some tests, but just to review here, what are we doing in this pass? This pass is about turning nested expressions into sequences of statements. So it's like selectively walking, and not just sequences of statements, but like labels that can be jumped to. So you don't have nested expressions. You have sequences of assignments and jumps with comparisons. So like that's the top level thing in here in your we need to handle this, by the way. A read in effect position. So we need to go in here. This in effect position is going to be a sequence of read statement followed by the continuation and blocks. Okay, that was something that they called out, like, because this is about the side effect of the read, even if we're assigning it to nothing. Okay, so to review, there are 4 types of things we have to handle. There's tail position, which is the return value of the program, and anything that is inductively in the tail position. There are assignments, which is like a let binding or a set bang. And there are conditions, or predicates rather, which is they are the part of the if that gets evaluated to determine which branch to take. And then finally we have effect position, which is inside begin expressions. So we've handled all 4 of the cases, and now let's go and make a test. Okay, so let's see if we can rename symbol. No, it's not doing that. So let's change not that. lm if to lmon. And let's just replace all. And okay, it's just complaining about the stuff we don't have in here. Okay, so this is going to be, we're going to change this to C loop. This is going to change to L while. This is going to change to lmon while. And this is going to be lmon. I just want to make this consistent so that when we do changes like this again in the future, it's like replace some aliases at the top of the file. And then, you know, you don't have to do as many changes in the body of the file. Okay, so we need to change. Okay, oops. We're going to change L underscore if dot. Need to make sure I make that clear. Okay. Yeah, it's been imported twice. Can you do that? Yes, you can. Okay. All right, let's run this test. Okay. Line 236. We got a problem here. Okay, so we need to update this. Because we need uniqueify, and we need uncover get. Okay, so our test pass. That's good. That's good. Okay. We need to introduce some tests for loops. Okay, so this is going to be XPlate control. We need begins. We need while. These are going to require some crafting. Okay. I don't know that we need to handle get bang explicitly. Maybe we should cover it with some tests. But okay, so let's think about what would be a reasonable test. Let's write let x read begin right. Okay, let's think about this. getting turned into a why don't I make a helper like I did in the other test modules, like parsed. It's going to be input is a string, and then it's going to be a L while. Okay, we're going to say input should be okay. Parse dot parse. Should be okay. Okay. So we can say we can pass this to parsed. And then I think we want to get all the other phases. Yeah, let's go ahead and pass it to okay, now the question is, can we construct what we think that this should be? Now what we could do is do that at first. Do we have Gleam IO imported? Yeah, okay. So see what the output program is. Oops. Yeah, let's go, those all have to-dos. Okay, so, oh, I have some parsing problem in here. This needs parens there. Okay, so we have uniqueified, so x.1. Interesting, uniqueify doesn't handle setbang. We have a bug. It's good that I'm passing this through. Okay, so this is actually not that surprising. It didn't transform that much because there weren't any complex operands. But what we need to do is update uniqueify to handle setbang. There is a problem here. Oh, okay. So yeah, we need to introduce this get var. So this is get var variable env, right? No, it takes env first. That should fix this problem. Okay, now it's setting the correct variable. That's good that we found that. Okay, so interesting. Now that it has that, it's recognized that this is the same variable, so it's introduced the get bang. Okay, so let's copy this out. And I think that what we'll do is we'll do one test. We'll finish this test, make it pass, and then we will okay, I'm going to let it pretty print that and then comment it out. This is what our input is, right? This is the result of all of this. That's P. So what do we expect this to transform into? So we want a C program. Did I import that? No. Okay, that's fine. So we want a C program, and this needs a tail, so it's going to be a sequence. Nope. And that's going to have an assignment to x.1, and then that needs to be an expression. Prim is an expression. Okay, and then that has another tail in it. So we read into X. That has another sequence in it because we're going to do this is going to get lifted. Right, this let. Okay, so we did this first assignment, and then we do this assignment, and then we're going to assign back to x1. So the tail here needs to be another sequence. Okay, so now we've got that set bang handled. And then this is going to be another sequence because we need to assign to temp2. You know, this is a little bit inefficient because we are assigning to and then reading from variables that are the same. There might be a way that we can not introduce those, but let's see. Okay, so finally we will have, this is tail position, right? Because it's the tail of the begin, this let. So inductively, this tail of the let is the tail of the program. So return is going to take an expression. So primitive plus variable temp.to, and then finally int 42. All right, what's wrong? Expected two arguments got one. Oh, right. So C program has a body and an info. So this has no branches, so it's not going to create a block. So this is going to be the second part. Here, let's go to that definition. Okay, so this info, yeah. And then let's wrap all. Okay, it's not correct yet, but let's wrap that in square brackets. Curl. All right. Okay. Wow. All right. So I hope you can see this in the Elmon while the monadic form gets translated into this. And you'll note that, like, although we are treating this as a sequence of expressions, the sequence is like const cells. It's not a list. It's like, here's the thing, and then you go into the tail. And here's the thing you do, and then you go into the tail. And here's the thing you do, and then you go into the tail, and so forth. So we're still kind of in a functional type of structure, but let's see. Explicate control, please. Should equal P2. All right, let's see if that passes, and then we can call it a day. Okay, and our failures only happen from to-dos. So I'm going to comment those out, and we can do those next time. Okay, so we got pass. Okay, good work. Thank you so much for bearing with me. I think that we learned a lot today. And we'll be in a good position next time to go down a layer and start selecting instructions, which will be super fun. So I know that we still haven't gotten to the issues that we need to adjust the control flow graph for, because that happens in the allocate registers phase and the phases that support that. So we will have to deal with that next time. Also, next Sunday, a week from today, I'm traveling in the afternoon. So if we do this next week, it'll be on Saturday. So be aware of the time change, and I'll make sure to schedule that on my YouTube channel so that you can attend if you want to on Saturday. Anyway, thank you all for coming, and we will see you next time.